Now turn to reviewing the basics of fluid hydraulic systems, and let's hear some figures from typical kind of fluid mechanics problems as you might see in an undergraduate mechanical engineering course in the area of fluid mechanics, where you're interested in storage and transmission of fluid. There's pumping problems, losses in lines, and so on. Those are kind of the concepts that I'll expect that you will be familiar with. Maybe you've applied them in a course like in a system dynamics course before. So those are the principles that we'll be reviewing briefly here. I'd like also to maybe bring in some examples later in the way of problems and applications to hydraulic and hydraulic power, showing here some pistons and hydraulic motors, but also think about how these are also principles used in modeling other kinds of fluid dynamic systems level problems. For example, here's a model of the cardiovascular system and how power in the form of fluid is transmitted throughout the human body. So these principles can all be used for different types of physical systems of that sort. Reviewing now the potential energy storing element in hydraulic systems, fluid systems. The principal state here is a displacement state, which we'll choose as the volume, okay? Which means we're going to want a constitutive relation that will give us pressure as a function of that state, which is the volume state, right? Remember that we can then compute potential energy as a function of volume, right, given that we know the pressure. And if we have a linear relationship between pressure and volume, we can sometimes express this almost like a capacitor, where we have a hydraulic capacitance. Okay. Now, in those cases, you can see this corresponding energy relationships in terms of the capacitance as well. I've shown one schematic here for a typical tank where we might have fluid coming in. Remember that the flow that we're thinking about here is the flow that sort of goes in to store volume. So the key relationship is that the rate of change of volume, right, is that difference in flow. So this is a lot like a capacitor in a sense, if you think of it in the analogy of this being the difference in currents going into a capacitor. We are making the assumption that the pressure is common across here. Again, there's a lot of different kinds of capacitive elements to be concerned with. Again, these could be constant area tanks. These could be a lot of different types of tanks. You might have vessels that are not necessarily uniform constant area, circular, but also you can have hydraulic capacitance in some pipes or some vessels where actually you may have expansion of the actual vessel itself. So you can have potential energy not only because of energy stored in the in the fluid. Here again, you're not accumulating fluid, but you could actually have compressibility, right? And this becomes especially important in some hydraulic systems, but also sometimes the actual the actual pipe, say, can sort of breathe, and so you could think of energy being stored in the vessel of the itself. So we'll look at maybe some examples like that. Okay. So again, the rate relationship that allows you to write a dynamic equation is the rate of change of volume. We have storage of potential energy and the formation of a fluid inertia, and here's a schematic showing that you might have a pipe. And so what we're talking about is analogous to any kind of mass. You have fluid mass now, and as you try to accelerate that fluid, right, you're going to have momentum. We're going to use the symbol gamma here as a fluid momentum. So we have a constitutive relationship between the flow rate and this fluid momentum. If we have a linear relationship, which is very common, then we can define a fluid inertia I. For a typical pipe, if you have a pipe segment, say, length, let's say that's some area, and let's say the fluid is incompressible, the fluid inertia for those cases can be easily computed given the density, the length, the volume, and the area. Okay, talked in previous reviews about how this parameters, right? Like remember for electrical systems especially, you can always think of these being as sort of related to the sort of the material properties and the geometry of the element. So here the length and the area play a key role. The dynamic relation here, as you can see, is that the rate of change of this gamma, right, this gamma dot is the difference in pressure wanting to accelerate that fluid. I'm going to show you shortly where that term comes from. Sometimes, having gone through a fluid mechanics course, this is not apparent. This is not a term that's often dealt with. A lot of times we deal with sort of steady state problems when we're looking at so we say losses in piping systems and so on. Again, all the typical energy relations are here. Remember, this is a kinetic energy storage element, so these are kinetic energies and kinetic coenergies that you can compute if needed. Okay, and here's your linear constitutive relation. The hydraulic resistor is what really makes, I think, the study of fluid systems interesting and a little bit more complex, even though we can make a nice analogy to sort of a resistor. And in fact, there's a real nice analogy between hydraulic systems and electrical systems, and sometimes you'll see electrical systems introduced as like fluid networks to build that analogy and make it easier to understand electrical systems, and sometimes it's the other way around. We'll think of hydraulic systems almost like electrical systems. So capacitive elements and the inertia, for example, is analogous to the inductor. And those analogies work well to a certain extent. There's some things that can happen in, of course, both physical areas that are unique, especially in if you think of flow in fluid systems where you have the ability for the fluid to become turbulent. So this nice analogy sometimes can break down. Remember, resistive elements are dissipative, so their power is always being dissipated. And here, for example, you have a pressure drop and flow through here, so that power dissipated would be just that product. Again, it's generating heat. You know, if you have a valve here, this guy can be getting hot because there's heat transfer off of it. If you have a linear relationship, that occurs sometimes if you have laminar flow, cell flow. And in that case, it's, you can go back and review your fluids textbooks or any books that you might find. But in this case, that resistance, you can find is easily computed again from the physical, the geometric parameters, and mu here is the viscosity, the dynamic viscosity. So as long as the flow is laminar and hasn't turned turbulent, then this analogy of a linear resistance is good, or rather this constitutive relation. But if you have turbulent flow, which, remember, is going to depend on the Reynolds number, so you always have to compute the Reynolds number. And if the Reynolds number, say for a pipe, sometimes we say maybe anywhere from 23 to 4,000 Reynolds number. So sometimes in a fluid system, you have to be checking the Reynolds number. If it trips to turbulent, then this constitutive relation is going to become nonlinear. And I'll include some discussion problems or some homework problems where you can investigate that. But now your constitutive relation between pressure and flow can become nonlinear. So, for example, you might have another coefficient. Let's say that's some other coefficient that's not necessarily the same as this r. But now that relationship with with flow rate can become quadratic. And actually, often we will, instead of using q squared, we'll write this as q times the absolute value of q. And there's some benefits to doing that. Instead of using a quadratic, which is not a symmetrical function, we may use something q times q, but with an absolute value. This gives you sine, right? Think about when you plot that, right? Then it looks quadratic on this side, and then it's quadratic in the first and third quadrants of that function. Anyway, I'm plotting here P versus Q, right? So this is like a turbulence function, and this is a laminar function. Let's turn now to reviewing ideal and real, as usual, power sources, now for hydraulic systems. Again, in the simplified cases where we want to just represent pressure sources and flow sources, remember a pressure source is going to be a system that prescribes some kind of pressure as a function of time, regardless of what kind of flow you have. And here, typically we're talking about pumps, but you can also be talking about, let's say you just had a pipe that was just, emptying into atmosphere, because, you have flow coming out of this pipe, say, you may put a boundary on that and say, well, that pressure here is a source, and no matter what that flow rate is coming out, I'm always going to have atmospheric pressure as the source here. So there's a lot of different ways. It doesn't have to be an active source like a pump of some type, but here again I'm showing the ideal, and then a lot of pumps might provide pressure, but as you do start pumping at higher and higher flow rates, that pressure can taper off because you have a real source. So again, we'll work examples that allow you to use and understand why these trends might occur. Pumps also provide a source function in terms of flow rate versus pressure. Similarly, you might have, again, an ideal pump that provides a flow rate regardless of what the back pressure is, but often a lot of these pumps will have characteristics that depend on the particular type of pumping mechanism that you have. I wanted to bring up one other topic that I'd like for you to think about whenever you're modeling fluid systems, and where especially that inertial term comes from, basically the storage of kinetic energy. Typically, what you will study in a fluid mechanics course is by studying and integrating Euler's equation, which is a momentum equation from the Navier-Stokes. You typically will make the assumption to get to the Bernoulli equation that you have. You recall the assumptions. It's a steady flow, streamlined flow, right, and inviscid. So there's no losses in there, right? There's no, and if when it's steady, it means that you don't have any inertial terms either. So typically, I'm pulling out here, there's a term that you kind of throw away there, and that's this dynamic term. You see this has a derivative of the velocity along the streamline with respect to time. This term right here, if you look at all these terms here, they're actually pressures scaled with density, just because of the way the Bernoulli equation is typically written. There's a velocity term here. Remember, these occur because of changes in area, right? So these could be like your static pressures. Here's your dynamic pressure, right? And then here's a pressure that's due to what? Change in elevation, right? So this equation is very important for that reason, but a lot of times we ignore this guy. This one here, this is your gamma dot term, right? So keep that in mind. So this is kind of a nice analogy, and this is what leads to that typical relation. Remember, we always talk about, you have your sum of efforts equal to 0 in all your areas. This is the dynamic term. It comes from an unsteady Bernoulli equation. But oftentimes we have to treat certain terms differently. We usually will have terms from pressure coming in from sources, say from hydrostatic sources, but the dynamic sources have to come in from terms that we introduce due to rates of change of inertia. And then we may have to add sources that are due to elevation. And then these special terms here due to dynamic pressures may or may not be dealt with. So primarily I wanted you to think about, and you may go and open up your fluids book, look in the index and look up the Unsteady Bernoulli equation. You'll see a relationship just like that. That's where this dynamic equation comes from. The other equation that we're going to deal with, remember, is the sum of flows equal to 0, and that's a nice, remember, I like this one because it's an easy one to remember. It's, you have a control volume and you have flows coming in and out, and just like the current relationship, you have a point of, like a pressure node, and you have flows coming in and out. So the sum of flows, that's typically a lot easier to use. And where does this come from? Well, it just comes from your continuity equation. Mass continuity, if we have rho equals constant, then we can think of this as the continuity equation in terms of volume. Remember, one of these terms could also be the fact that you have volume accumulating in here, and that allows us to write dynamic equations, just like we did in electrical systems. Just one last note on the v squared over 2 terms in this unsteady Bernoulli equation. I'm not going to say a whole lot there, but think of those as dynamic pressure terms. You actually have to multiply it by rho to get actual pressure. This is, remember, pressure, the units is pressure per unit density. So when you need to include those effects in your model, and sometimes, recall you might have a converging nozzle or a diverging nozzle, and there's differences due to dynamic pressure across here, because even though, for example, let's say you had flow rate coming in here, that flow rate could be, if you have a flow coming through here, that Q is going to be the same, but due to the area changes, call that 1 and 2, the velocities are going to be different, and that's going to cause a difference in pressure. Sometimes you need to take that into account, and the way you do that is with this dynamic pressure difference. And so we're going to, at least for now, propose to use that as sort of an effort source. And we may look at that in some of the examples coming up on hydraulic systems, or we may look at that later when we talk a little bit more about how to build bond graph models of hydraulic systems. But don't forget that dynamic pressure term. A lot of times you'll see it'll be ignored in a lot of systems problems, but we may try to introduce it in some cases just for completeness.